In this section, we're going to talk about logarithmic functions, properties of logarithms, and getting used to the idea of converting between sort of logarithmic expressions to exponential expressions and exponential functions to logarithmic expressions. So first of all, what is going on with logarithms? So after you read this section, you would have seen sort of the fundamental property that defines them, right? So logarithms are the inverse functions to exponential functions. So the definition is the following. If you wanted to find log base b of x, it would be equal to y if b to the y is equal to x. Okay, so this is an if and only if, actually. So if I had this exponential expression, b to the y is equal to x, that's the same thing as saying log base b of x is equal to y. All right, so kind of see how they're inverses of each other in the following sense. If I look at the left side here, and I took the if I did b to the power of both sides, and then I get b to the y, and then b to this logarithmic expression. But that would simplify to x, because the exponential in this log, those are log base b, are inverse functions of each other. So that's the defining equation or expression, and we'll use that to convert back and forth between logarithmic form and exponential form, and vice versa. And then we have a bunch of properties. So before I go into this list of properties, let me just show you how you use this first sort of fundamental equation that's defining them. Okay, so let's say that you have 3 squared equals 9. Okay, and I want to write this equation in logarithmic form. So this equation, if my base, this is my b right here, this is b, right? This is y, and this is x, right? Do you see that I have this exponential equation over here? So what this is actually saying is log base 3 of 9 is equal to 2. Okay, in other words, 3 squared is equal to 9. So that's how I convert that into logarithmic form. In the next one, my base is right here. My base of the exponential is 10. This is my my exponent, right, y, and here is x. So then I have log base 10 of 0.001 is equal to -3. Okay, now your calculator generally has a log button. Now, I will point out that usually your calculator only has the standard log, which is just log without any base designated to it, or the natural log, which is ln, and we'll talk about that a little bit later. Okay, there is a property to convert from one log to other logs of different bases and so on. So we'll use all these properties. It looks a little bit ridiculous, but kind of let me go through some of these, and I'll point out where you might be able to use some of them. You might be able to use your calculator to evaluate them. For example, this one, you could use your calculator because there is a button, just log, and then if you punched in 0.001, it would give you this output of -3. But some calculators do have a base specification, so it might be like log base blah and then what it is, and then you would specify what the base actually is. If it doesn't have that, we're going to have to use this base conversion formula a little bit later. But let me go through these properties. So first one just essentially says that if you have a log of a product, then you can break up that product as the log of the sum of each of them. If you have the log of a quotient, then you would break that up as the log of the numerator divided by the log of the denominator. If you have the log of an exponential, x to the m, then, well, it's really a power function, but anyway, it doesn't matter. It could be exponential power function. You can bring the exponent in front of the log. So this actually just goes out in front, and it becomes this m log base b of x. See that? Log of the nth root of x to the m, we could rewrite, remember our rules of radicals, as x to the m over n, right? The denominator becomes a root. And then using this property right up here, we can actually bring this out in front and get m over n log of the x here. And then this last thing looks a little bit confusing, but what it actually is saying is I'm converting from a log base b of x to logs of different bases. The way that you do that is you convert to any base you want, a. You would make this quotient, log base a of x, whatever the same input is, and you would divide by log base a, so these have to be the same, of whatever your original base is. So this is one way that you can use your calculator, because a lot of times it has this natural log, and this ln is that is the log where the base is that special number e that we've been talking about. And we'll come back to natural logs a little bit later, but this is how you could actually use your calculator if it doesn't have a base, an arbitrary base input. You know, you can convert it to things like this. We'll use these properties when we need them, but I just want you to be aware of them, and you should have seen them in the text already. Or if you haven't, then you'll see them in other sections later, and we'll only use them specifically when we need them. Okay, so going back, for now we're just really using this first one. So let's now convert expressions that are logarithmic into their exponential form. I think this is actually a little bit easier, to be honest, if you start with the logarithmic expression. So log base 2 of 32 is equal to 5. Well, then this is your base right here. Okay, so you have 2 to the 5th is equal to what your input is, the 32. Okay, so 2 to the 5th equals 32. And of course, whatever you're writing as your exponential should actually make sense. See, it's a little, you're more familiar with the exponential at the moment, but you'll see soon the power of the logarithm. I mean, it is the inverse of the exponential, so it should help us with a lot of things like simplifying and also solving exponential equations. So log base 7 of 49 is equal to 2. This converts to 7 squared is equal to our input of 49. Okay, and that makes sense, so that must be the right conversion. Okay, now let's solve each of the following equations for x using our conversion equation that we were just talking about up above. So log base 4 of x is equal to 3, becomes 4 to the power of 3 is equal to the input of x. And so now we just have to simplify this. Well, 4 times 4 is 16, times 4 is 64, so 64 is equal to x. What about this one? X to the 4th is equal to 16th. So if I want to solve for x, how do I solve for x at this point? Well, if I have x to the n, do you recall? X to the n is equal to a, then what do we do in this situation? We take the nth root, right? However, if n is even, then what do we get? We will get, we'll actually get x is plus or minus the nth root of a. If n is odd, the reason for that is this would actually become an absolute value, but if n is odd, then you just get the positive one. Okay, so over here we have n is even, so we're going to take the 4th root, so we'll have x is plus or minus the 4th root of 16. And can we actually figure out what that is? Well, 16 is actually 2 to the 4th, right? If you factor this, it's 2 to the 4th, 2 times 2 times 2 times 2 times 2 times 2, right? So that's actually just 2 then, plus or minus 2. Okay. However, Okay, so that's how you would solve it algebraically, but we don't actually allow a base of, we reject negative bases. Okay, we don't allow that, so x has to be 2. Okay, which is valid, right? 2 to the 4th is 16. Okay, now how do we graph logarithmic functions? Well, we could set up a table, right? Just like we've done before. So y is f of x, and that is log base 3 of x. Now, what are going to be some easier values to plug in here? Well, you do have a calculator, but I will say that plugging in the following values will make things a little bit easier for you to figure out. So if you plug in 1/9, 1/3, 1, 3, and 9, our lives are going to be a little bit easier. So what is this? So this is log base 3. Let's start with this one. Log base 3 of 1. Well, what is this? Well, 3 to what power will give you 1? Well, 3 to the 0 is 1, right? So this would be 0 then. 3 to the 0 is 1. Log base 3 of 3. 3 to what power gives you 3? Well, 3 to the 1 is equal to 3. Okay. Log base 3 of 9. 3 to what power gives you 9? Well, that would be squared. So you see, that's why I chose these, because I know that you're going to get integer values here. What about this one? Log. Okay, so log base 3 of 1/3, which is the same thing as log base 3 of 3 to the negative 1, right? Well, now that actually kind of answers it for you, doesn't it? 3 to what power gives you 3 to the negative 1? That would be negative 1, right? 3 to the negative 1 is 3 to the negative 1. So actually, this is really good because you can also see how they're annihilating each other. Log base 3 of 3 to something. Those two kind of annihilate and you get the exponent there. What about log base 3 of 1/9? Well, that's the same thing as log base 3 of 9 to the negative 1. And 9 is 3 squared. So that should help you here. 3 to what power gives you 9 to the negative 1? Maybe it's a little easier if I actually simplify that. That's 3 squared to the negative 1. So that's negative 2. And now 3 to what power gives you 3 to the negative 2? Well, that'd be negative 2. Okay, so now we have some points, right? So our coordinates for our points that we can plot are the following. 1/3, negative 1, 1, 0, 3, 1, and 9, 2. So we can plot all these points, right? So 1, 0 is right here. 1, 2, 3. Well, you know what? Since this goes up to 9, it's going to be off of this scale, right? So let's do this by 2s, actually. Okay, so let's say that that's 2, 4, 6, 8, 10. Okay, so 2, 4, 6, 8, 10. Okay, so 1, 0 will be right here. Then 3, 1 will be right here. And then 9, 2 will be right here. And then the 1/3 negative 1 be like here. So, and then whoops. So you see what's actually happening is it's approaching 0 when you get close. Sorry. Okay. First of all, as you input larger and larger x values, it gets larger and larger, but very slowly. You see that? And then as you get closer and closer to 0, these inputs get closer and closer to 0, the more and more negative it actually gets. So you sort of get this vertical asymptote here. And the reason for that is actually, let's see what happens if we plot y equals x. You will get y equals x, right? So there's our graph, okay? Whoops, there's our logarithmic graph. So this is f of x. But do you guys remember that if we wanted to find the inverse function, that we would actually reflect all of these points across y equals x, and we would actually get the inverse function. And what do you think that'll actually be? You know what? Let me switch to a different color. See, if I swap, if I mirror all these points, what am I actually getting? Do you guys see what's actually happening here? So if you flip all these, so 0, 1 gets you here. 1, 3 gets you here. Right? Is that right? Oh, sorry. This is by 2's, right? So 1. So this is 2, 4. So this is 3, right? So 1, 3 will be right about there. And then 2, 9. Okay, so you see it's growing very quickly. Then it does this. So this right here is actually the inverse function. And the inverse, I was saying that the inverse of a log of base b should be b to the x, right? That's the way, or b to the, see way up here, y equals, so here's your logarithmic function, then it should be b to the y is equal to x. Okay, so the inverse function here will actually be 3 to the x, and f of x was log base 3. Okay, so log base 3 of x. Okay, I just wanted you to see that. It didn't ask you to do that, you know, sketch the inverse, but I just wanted you to see that and how they are really inverses of each other. Okay, so continuing on, can we simplify the following? Well, 3 to what power gives us 9? Well, that's 3 squared, right? Since three squared equals 9. Okay, 10 to what power gives you 10,000? Well, that would be 10 to the 5th, right? So since 10 to the 5th is 1 followed by 5 zeros, if I, whoops, followed by 4 zeros. Oh, I screwed that up. So this would actually be 4, right? It's 4 zeros. Since 10 to the 4th is 10,000. Okay. All right. 10 to what power gives you 1? Well, that would be 0, since 10 to the 0 is equal to 1. 10 to what power gives us 0.0001? Well, this would be -4, since 10 to the -4 would be 0.0001. All right, so let's look at this one systematically. So log base 5 of log base 32 of 2. So let's look at the inside first. So if you wanted to solve this, log base 32 of 2 is equal to y, then that means you have to figure out 32 to what power gives you 2. Well, we know that 2 and 32 are related, right? Because 2 to the 5th is 32. So how do we get a power of 32 to get us this 2? Well, you could take the 5th root of both sides. And then you would get 2 equals 32 to the 1/5. So that solves this right over here, right? So log base 32 of 2 is equal to 1/5 since this is true. Okay, so now we have log base 5 of 1/5, which is log base 5 of 5 to the negative 1, and then that's negative 1 because 5 to what 5 to the negative 1 gives you 5 to the negative 1. So that's it.